to entire screen, my second screen, and let me check some settings. I prefer to change my background, some nice background. Okay, let me finish the setup here. I want to see myself in this screen and the slides on the other screen and see all the students in on another screen. This is good. Finally, the recording have started. Do you see the slides? Do you have a problem from my side?
No,
Is there any?
so
Good,
no
good.
problem.
That's finally you got it right. It was a good suggestion from someone, I'm not sure who was that guy, to change the browser. It's a browser app. There are many applications, browser applications. Even nowadays, many Android and iPhone applications, actually they are browser applications. They make a copy into your home screen, but actually they will not work until except there is like an internet connection. There are many frameworks, JavaScript. I'm not sure whether you are familiar with programming. JavaScript, the programming language, they use it to do a lot of things in the browsers. So we'll talk about some new technique called seismic reflection. The difference is big between refraction and reflections. Reflection is very important in oil industry. Is the main method used in oil industry. Almost like 95% or even more of the time, the method which is or geophysical methods used in oil industry is seismic reflection technique. It's easier in terms of application. There are not much caveats the one we have observed with refraction. The main drawback of refraction technique is that it will not work whenever there is a velocity inversion of a higher rock having a higher a lower velocity rock having a higher velocity than deeper rock. So well, this is something we call velocity inversion. It will not work, or we cannot do any processing or acquisition or even modeling if that's the case. However, in seismic reflection, there is no problem. Seismic reflection technique. I would like to ask a question. What do you see? What the picture shown to you in this slide? What do you think is this? Who can answer? Who can answer me? Anybody can volunteer and give me an answer.
Houston Graben.
There are traces. Yes, Ryan, there are traces. And someone is talking. Let me see. Who was talking?
Malik.
Malik, what do you think? What is this?
Said the horses and Grabens. The structure.
Amazing. It's a structure. It's a geology. This is a geology. I'm seeing some geology, but really this is a seismic section. This is in reality is not geology, it's a seismic section. They obtained this section with seismic reflection technology. They deploy the seismic reflection acquisition, and the final output is this seismic section. I'm seeing the one of the axes is the depth or time. On the other hand, the other axis, the x-axis is the distance. So usually they say how much the distance is one trace to another trace. These are traces usually, and I'm displaying them in a way called variable density. What is variable density? Is a technique of displaying seismic data, seismic reflection data, wiggle display, variable area display, and this is what we call variable variable density, sorry. But the most important thing is what I can observe from those sections, what geology they can infer to me, what they portray to me in terms of structures, folds, layers, trace, things like related to geology. Basically, these are all traces. There are multiple traces. So we'll talk about seismic reflection technique. Whenever I talk about seismic reflection technique, something else comes to my mind which deploys or use the same technology. It is called GPR. The guy who is holding this equipment, the equipment name is GPR, ground penetrating radar. The final outcome from this method is similar to what you see of seismic sections. So this is a GPR. The small inset figure here you see is called a GPR section or GPR image. It's an image of GPR. You find there is a great similarity between this small inset figure and the large figure, background figure you see behind. I'm seeing some reflection, some stronger amplitudes and some low amplitudes. So this is a strong amplitude you see, for example, let's say here, this is a strong amplitude. Here, this is a strong amplitude. It means this rock has a higher density and a higher velocity. The reflection is strong. The energy, a great amount of the energy is reflected up because this layer here, the geologic layer, has a higher density and velocity. And what else I'm seeing? I'm seeing like some grabens, salt domes. This is a salt dome going up. This is another salt dome. So seismic reflection in terms of method or processing is similar to something called GPR. We might study GPR in this course, just one lecture. We'll not go into depth or details. We call it rattle. The method, the technique is rattle. Why is that? Bats send sounds, and that's how the bats hunts, and that's how they can see or sense during the night. They send waves, and the way they wait for the wave to reflect back to their ears, and that's how they prey. They know where is the insects and go eat it. We do something similar. We send the waves and wait it to be reflected back to the surface and recorded by another instrument called geophone, usually in the land data, and hydrophone in the marine data. So seismic reflection method is a dynamic technique or geophysical method. Usually the source is either a vapor or a dynamite. We lay out a lot of geophones on the surface and wait for the signal to be received. It's mostly used in oil and gas industry, and that's the reason I'm trying to like spend almost 3 weeks, and we'll do a lot of labs. I will give you also some assignments regarding seismic reflection technique. Your first project will be related to seismic reflection technique. In oil industry, the final outcome is something what you have seen in the background figure. That's what we call seismic section. It's called seismic section. Geologists and geophysicists, what they do usually, they spend a huge time in oil industry tracing or picking these traces. What they do, let me do it together. It's automatic process, by the way. Yani computers nowadays are smart and they can guide you, they can help you how to trace these reflectors. So this is a reflector. What the geophysicists do, or geologists, or even sometimes petroleum engineers, they go along this trace. Oh, I'm not sure it's Let me delete it. Erase all ink. So this is how is it. They do a lot of picking. Can I increase the size? Not sure. Anyway, you see those points. They go and pick it. It's going up and down, something making something like that. This reflector might be the top of the reservoir. So why I'm picking it? I'm interested on the reservoir where the oil is. The oil is contained in a rock called the reservoir. I try to pick it and find where the oil, what is the structure of this surface? What is the depth of this surface? That's the reason I'm picking it. When I pick it, I will pick it in multiple lines. This is one section. I may pick it in many sections. And once I finish the picking, I produce a map. I produce a map of the reservoir structure or depth map. It's initially in time because in geophysics, what you do, you send the energy and wait for the energy to be retained and recorded. You are waiting. Whenever there is a wait, a term wait, it means I'm referring to time. But we need to find the velocity. That's the main advantage of seismic. Seismic can tell you how to know the velocity. And we spend a lot of time trying to get the velocities of those reflectors. How much time it takes, it depends on the velocity. How fast is the P wave or S wave? Which usually we are interested only on P wave. So those sections are changed in amplitude of waves of P wave, of the P wave energy. The amplitude of P wave, because first arrival, it's easy to be recorded. There might be some S, but will not process them. We try to recognize them as noises. Surface waves, all the surface waves, there are a lot of noise associated with them. We consider them all as noises. And we spend a lot of time in seismic data processing, try to remove surface waves. Surface waves are Rayleigh or Love waves. So we try to get the velocity. We generate the final outcome is a surface map. The petroleum engineers in their final year project, that's what they get. They get a surface map. Let me mute this thing. Not sure what's on. So what you get as a petroleum engineer is a map, a structure map of some reservoir. Your task is to check it first, observe it, try to generate something called GRV. If you are not familiar with these terminologies, don't be afraid, because I'm not questioning you. I'm just trying to tell you information. They might come to you later on. So we try to get something called GRV, gross rock volume. So if I assume this is a dome, like dome, this paper is like a dome. The oil will be trapped here. This is the reservoir. Above the reservoir, there is a sea rock, a rock of low permeability and low porosity, which is called sea rock. The GRV then is the rock volume, the volume of the rock, how much in square, not square, square, or cube, not square, actually, is cube. Volume is meter cubed of rock is there above the oil water contact. So you try to get the rock volume and try then to guess how much oil you can produce from the reservoir. So your first project, the team project, is related totally to picking, the thing I did. So this is a picking. I go here, map it. There is something wrong with my slides, so it goes, create some spike to what you have seen. Ignore those spikes. So I create some structure. And I guess, okay, the oil might be here. So this is the reservoir. You are asked to create something similar in your project, but I will send you more videos letting you know how you do the interpretation, particularly for the seismic section or seismic lines. This is a seismic line or seismic section. We call it a line because it's one line, one section, a depth model of the earth. So we'll give you more details how you can proceed with the project and how you do the interpretation, picking, generating the maps finally, and calculating the GRP. Let's move forward. I can delete these things. Ground penetrating radar is utilizing the same theory in principle, but instead we are using not seismic waves, electromagnetic waves. So electromagnetic waves are much faster. In here, in seismic technique, the time usually in milliseconds. The maximum time usually is 6 seconds, 8 seconds for deep imaging, like up to crust, middle of the crust or lower part of the crust is not more than 10 seconds. So you see how waves are fast. In Oman, I haven't seen a section myself deeper than 4 seconds. Most of the sections, seismic sections, they are just 6 seconds. 6 seconds. The waves go hit like 4 kilometer deep or 3 kilometer deep and returns back. It's two-way time. It's not one-way time. It's the time the wave goes to the reflector, to some horizon, to some rock layer, and get reflected back. So we call it two-way time, two-way travel time. Whereas with the ground penetrating radar, the time usually in nanoseconds. The electromagnetic waves, they travel very fast. The speed of electromagnetic waves in the earth is really tremendously uh, fast. But in terms of resolution, resolution is a terminology in geophysics. We use it to tell how I can distinguish between two features close to each other. So two layers close to each other. Can I distinguish them as one layer or two different layers? If you cannot distinguish them, it means you cannot resolve them. That's what we call resolution. So in terms of resolution, ground penetrating radar has higher resolution, is very detailed resolution, whereas seismic reflection is of lower resolution. In overall, most of the geophysical techniques, the deeper you go, the lower the resolution. So if I ask you right now, I think you are following along with me. If I ask you this question, which of these methods can penetrate deeper into the ground? Seismic reflection or ground penetrating radar? Deeper, deeper.
Seismic reflection.
Yes, seismic. Who was answering? Who was talking to me?
Me.
Basma. Okay. So yeah, that's true. Seismic reflection goes deeper, whereas the ground penetrating radar does not travel deep. We have three in our department, three antennas of GPR. One of them is 100 megahertz. It sends a wave with a frequency of 100 megahertz. The other one is 250 megahertz. The last one is 400 megahertz. So 100, 250, and 400 megahertz. Three. Which one you think will go deeper? By the way, seismic, the frequency content of seismic reflection is not higher than 110 hertz, not kilo, only hertz. Whereas ground penetrating radars, the frequency of those waves, electromagnetic waves, are in megahertz. So back to my question, which of these you think will penetrate deeper? Ground penetrating radar of the antenna of 100, 250, or 400?
100.
Yeah, that's true, 100, because I already, some of you, Basma said that a reflection goes deeper. And we know the reflection, the frequency is low compared to ground penetrating radar. Whereas ground penetrating, it depends on the antenna. There is how deep you go. It depends on the antenna. It depends on many other factors too, but mostly on the antenna. You know, in many companies, and Oman at least, they do always, whenever they build a very important building or a building belonging to the government, they do testing to the walls. This is the wall of my office. They do testing to the wall to check how rugged it is, how the cement, how it's the plaster, at least how it's made. So they use ground penetrating radar. They use what? GPR. But the antenna is in gigahertz. It's not mega, then it's giga. It goes only like 4 or 5 inches. Goes deep up to 4 or 5 inches. Gigahertz. Cannot go very deep. But it gives you a very detailed image of the plaster. If there is a small bubble in the plaster, you can tell that there is a small bubble or the plaster is not made well. They use it. Even Omani companies operated by Omanis doing these things. Many of them, they were even not geophysicists. They know the technology of ground penetrating radar, GPR. So let me go to my slide. Unfortunately, whenever I'm in this drawing mode, I cannot go through the slides. So before we go, let's talk about seismic reflection in general. What seismic reflection and what are the differences between seismic reflection and refraction? It's the most important geophysical technique. It's the technique we use to image the Earth interior. It's the technique we use also to investigate deep and shallow investigation, for water investigation, for site characterization, for like landfill studies, for reservoir studies, oil and gas industry. It's very well suited for many applications. So as I said, it's massively used for oil industry. It's very good to investigate geologic features like stratigraphic faults, pinch outs, groundwater resources. It's so popular. It's very popular for many reasons. The main reason Malik said when I asked him, he said, "Oh, this is a fault. This is a syncline. That's I'm seeing a salt layer," because it produces the final outcome is something very which resembles truly the real geology. In seismic refraction, what we were seeing only TX diagrams, straight lines, not very useful. You do some processing and you find the final thing you find is velocity, is not a structure. Whereas in this case, we see structures. We are also not seeing only, we are not only interested in the first arrivals, we are interested in all of the arrivals. One thing, the arrival time, and we are also interested on the amplitudes. So the figure behind is telling something, the background figure is telling something about how strong are the amplitudes. So amplitudes are telling you some extra information. We cannot obtain that information from refraction technique. And that's the reason it's very important. It's very popular. It's very well used in many applications. By the way, the figure you see behind is a salt dome. That you see behind is a salt dome from Gulf of Mexico. Gulf of Mexico, most of the reservoirs are produced from salt. Salt is something which is incompetent. Whenever it's very deep into the ground, it becomes moldable. It becomes movable too. It can be easily molded, and you can make it in different shapes. And it tries to find a weak point in the rocks above to escape. So it deforms the rock and creates features like what you see. Can you see this feature? It's not very clear, I know. It's background feature. But I can show you, for example, Sol Doom Seismic. Oh, images. So here, and by the way, this is Oman. يعني قارة كبريت is in Oman. يعني they go get the salt from there. It's on the surface. It's some part of Oman. You get the salt on the surface. You go and try test it. You find it's very salty. And many reservoirs in Oman actually they are produced or they became reservoir because of the salt domes. Salts made those structures, reservoir seals, and helped to create hydrocarbons. So this is what we call a salt dome, basically. So a bit of history about seismic reflection technique. It became quite interested in or interesting in 1930s for basin analysis, sedimentary basin analysis, and for oil and gas exploration. The first case was in actually USA, in Texas, and it becomes popular because it produces seismic sections, and those sections are resemblance of the true geology. It's almost you are seeing a cross section of the subsurface. It produces very high resolvable or resolution data compared to other techniques. If I compare gravity technique, for example, the resolution is way higher than the gravity technique or magnetic technique. Magnetic and gravity technique, they will not produce an image, a real image of the subsurface, whereas seismic reflection technique does. And it's very important too because if you want to do the survey for oil industry using seismic reflection technique, your expenditure might be $15 million or $10 million for big area. Let's say 20 by 20 kilometer square. So 20 or 30 by 30 kilometer, that big area, it's big area. You might spend like 15 million or 20 million. Whereas one well might cost you, especially if it's an exploration well, might cost you 10 million. And you might get lucky, blindly drilling and get lucky. And you might not find anything. You find that your well is dry. Nothing except some water, salty water. And you cannot do anything with very salty water. You need to inject them back then to the reservoir or deep layers. We are interested in oil. But seismic data, they give you an image, a big image. You can tell where to drill, where I'm seeing some structures, like an anticline, like a stratigraphic trap. Those are the things I'm interested on. So geophysics is very important. Instead of going blindly drilling and wasting a lot of time, it's better to do some geophysical technique. And as I said, one of the technique which resembles truly the geology is seismic reflection technique. So what are the differences? Why we are interested in reflection? Why not continue with the refraction, a technique we used? Refraction is cheaper, is way cheaper. Refraction usually is only 2D. Refraction in terms of processing is easy, way easy compared to reflection. You did processing. Have you seen the software? This is easy software. I cannot get a software reflection processing software for you because those are really expensive. They are not free. And they need high computing powers. Your normal PC, simple PCs, laptops, they might not be capable of doing processing, seismic reflection processing. The final outcome is velocity. You get velocities from refraction. That's what we have seen. Layer, and each layer, what is the velocity? Whereas in here, I'm getting a detailed image of the subsurface, a very detailed image. Here, I need critical angle. So if my layer is very deep, the uncritical angle might be very high, especially if the velocity is high between these two layers. One layer, another layer, if the velocity contrast is quite high, the refraction angle is high. So you need, what you need your source and receiver to be far away until you get critical to the critical refraction, critical distance. Subdistance, you need to go beyond that distance. And for very deep, very deep layers, if you want to image them with seismic refraction technique, your geophone and source, they must be in different countries. They need to be in different countries. Whereas for the reflection, no, they can be just adjacent to each other. The ray goes and reflects, goes to the layer and reflect, where the geophone, the source and receiver are nearby each other. Do you remember when I said, if I want to go a depth of 5 meter for seismic refraction, 5 meter depth, what is the optimum spread length for the case of refraction technique? What is the optimum spread length? What is spread is the spacing from first to the last geophone. If I want to image 5 meters, who can answer me? For the refraction technique. Are you guys with me? سؤال.
Again, Doctor, the question.
Okay, Basma, the question says that if I want to image up to, let's say, 10 meters using seismic refraction technique, what is the required distance or length of my seismic refraction spread? Yes, so 10 times that distance. If I say I want 5 meters, the distance from first geophone to the last geophone, if I'm using 24 geophones, as is the case with our equipment in our department, the refraction technique, or I forgot the name of the equipment, but the total number of geophones it accepts is 24. So I have to make this distance, the total distance, 10 times my depth of investigation. If I want to go 50 meters, 50 times 10, 500. I have to have my geophone spread 1, 2, 3, 4, 5 distance from 1 to the last number 24. How much I should make it? 500 meters. Whereas in the reflection technique is 1-to-1 relationship. If you want to investigate 1 meter, 1 meter, make your distance from source to 1 meter. And this is the drawback. These are all advantages. 1, 2, 3, tick, tick, tick. This is cross, cross, cross. Oh, sorry, these are crosses. These are green ticks. The first 3, because those are advantage with the reflection. The disadvantage or the drawback is the last item, the last point. Here, processing is easy. I'm interested. I like to do some easy things. Whereas the processing with seismic reflection technique is quite cumbersome. Is not easy. It's difficult. Yeah, that's what. So the depth of interest, يعني the spread length supposed to be 5 to 10 times the distance. Why 5? Let's you can make it 10. Oh, sorry. Are you happy? So 10 times x. What is x? Depth of interest. X is depth of interest. This is the spread length. Capital X is the spread length. Is that fine, Ryan? Is it understood to you? Yes. Fine. So it's not, I just made it 10 to make you in the safe side. That's the maximum, but you can make it 5. It depends on many other parameters, the velocity contrast between two or many rocks. So we see that reflection is advantage to the refraction. The only thing is processing. There are some saying that 30% or 20% of computer powers nowadays used in processing reflection data, and that's true. There is a company in Oman called CGG. It's a French company. Some people are boycotting French companies nowadays. They are not trying. They will not buy anything produced by French. So this is what we call boycott. It's a French company. It's operating in Oman since a very long time. It's one of the most powerful processing companies in the world. If you go to their offices, the first thing which catches your eyes is the computer clusters they have. They have big, powerful computers. Those are very expensive, actually. They are really, truly, truly expensive. So my computer, this PC, it has, let me show you. I will show you how many processors I have and how many RAM and many other things. They're waiting for it to appear. Why is it taking too much time? Anyway, yeah, that's it. Do you see this thing? So if I go to processors, how many processors I have? How many cores? 6. 6 cores. Each of these core can do 2 things, and that's what they call it threaded, multi-threading. So the total different job my computer can do at one time is 12. So each processor, each core can do graph to overall utilization, or whereas the computers there, they are made of hundreds of cores and clusters. So one computer have probably 120 or 128 cores, and it's connected to another computer, and they are working together to do seismic processing in the company, CGG company, or in PDU. They have 2 offices, one global office in Oman. They are receiving data from everywhere and doing the processing here in Oman. Another company is based in PDU. Their office is inside PDU. So they are doing all the processing for PDU, and they are always busy. So processing is quite difficult. And how it works, why it's very important. It's similar to echo sounding. You're sending something and receiving the echo. So let's assume that a ship is traveling in one way, and the ship sends a wave, a pressure wave, because I'm in sea. Uh, what is the wave type I can receive in sea? Body waves, a type of body wave I can only receive in sea. The other wave type will not be traveling in sea, in marine. A wave type, a body wave type, which cannot travel in marine. What is it? There are two body waves. One is P wave, the other one is S wave. Can S wave travel in sea, in water? No, the S wave cannot travel. So P wave travels because it's pressure wave, and they can change. I do compress the water or the liquid in general. Even gas can be compressible. But water is not shearable. You cannot break it. You cannot. ممكن أكسر الوتر? No, you cannot break it. I have never seen a fault in the water, but rock can be faulted. Shearing force is not applicable on water. So the source usually in marine is an air gun. It's called air gun. Why it's air gun? The air goes to some chamber at high pressure and releases suddenly. Suddenly, the pressure is released in the water. And the change in pressure moves every direction. It hits the ground or sea bottom. That's the sea bottom. The energy reflected. Some of part of the energy is reflected. Some other part transmitted. So I received the question, what is the reflection, but what is the difference between reflection and transmission? Actually, they are the same. The energy will be reflected and transmitted to the surface. Sorry, reflected and reflected and refracted. Transmission always happens. Transmission is similar to refraction, but transmission is not similar to critical refraction. Critical refraction happens only at critical angle. And that's the energy. Critically reflected energy is the one we need to do refraction, seismic refraction technique. I received a question by email from some students. So what I receive some wiggles. So if I'm recording and I'm traveling from here to here in this direction, each time I send an energy and wait for the energy to be received, how many pulses you think you will get? How many pulses are they gonna be if you keep recording? This is a pulse. This is another pulse. They're gonna be 3 pulses because there are 3 reflectors. 1, 2, 3. Which pulse arrive first? These pulse arrive. These reflections arrive first. The energy goes down and reflected back. I move a distance to the left and do the same thing. Send the energy, wait for the energy to be received back. And I keep doing the same thing. You get an image similar to you see here. Pulses. Each change indicates a change in acoustic impedance. What's acoustic impedance is, by the way, another change with the refraction and the reflection. Refraction does not care about rock density, only change in rock velocity. Whereas reflection, this thing, or reflection, it cares about 2 things, density as well as velocity. So I generate a lot of pulses. This is what we call a trace. Ryan was saying These are traces. Yeah, the figure you see behind those are traces. So I record many traces. If I complete all of them, you'll find a section. This section is indicating something, is telling you an information about the subsurface. The first one is, or the first pulses or ray of pulses from each subsequent traces tells you how deep in time is the seabed is. How deep from the subsurface, from sea surface is the seabed, but in time. Then the first, second reflection, then finally the third refraction. And that's what we call echo sounding. And these things, we call them reflections. What we call them? Oh, I probably need to change the background because this thing happened. The background is an image. They are reflections. In time, they are called reflection. Once I do velocity conversion, and I convert from time to depth, I call them reflectors in depth domain. Whereas reflections, they are in time domain. So there are some caveats. We need to think about them, and we need to do some processing to understand how to overcome these problems. The first thing is, as we have seen already, the vertical scale. In what domain is it? الريم شحية. الريم الشحي. Are you with me, Reem? What do you think is the y-axis or vertical axis in seismic, in the domain or in the section you have seen here? What domain is this? Reem? What domain is this? Can you write? No, it's initially time domain. Because you send the energy, you wait for the energy to return back. You wait. You keep recording the time, how long it takes to return back to the surface. So the vertical scale in seismic reflections is time. Velocity, as we know, is not a constant, is not a single velocity. Each layer has its own velocity. So the depth conversion, converting from time to depth, is not easy formula, is not something you just multiply by a number, by a scalar. It's a complex process. It's a really complex process. Quite complex process. We'll not do it in here because students will do it in seismic data processing course. So this is a complexity, but we'll go through this one. And we, as a geophysicists in our industry, we can overcome this problem. It's, however, a caveat. It's not an easy thing. Another thing, reflection usually they not come directly from below. What's that? What I do mean by that? I mean that snipping tool, because let me create a snipping tool. So here, let's assume that this is surface of the earth and this is a reflector. If my source is here, I'm shooting from here and this is the receiver. source and receiver. What do you think happens? It might go like that and return back. That's how it goes in reality. But you will see it's like that. You think the subsurface is here in the middle. You think it's in the middle. But in reality, it goes here and hit the subsurface at right angle. That's what we call Fermat's principle. Is it written here, Fermat principle? No. That's what we call, again, I simplify because I think you got frightened here. Usually, whenever, or make it a bit more simple, let's make it more simple. I give you another simple example. Let's assume source and receiver at the same point here, close by each other. And I have a reflector, something making an angle. So this is one layer, layer one, and this is layer two. What do you think? You think it goes like that and get reflected to the surface. That's not true. It goes this way. It goes here and reflected back. This is right angle. What do you think really? Yani, you doesn't know. You think it's coming from below, midpoint below here, but it's coming midpoint between source and receiver. That's the midpoint between source and receiver. But it's actually coming from straight perpendicular line, head line. If they are on very, very close by, source and receiver are adjacent to each other. So this is some drawback. We can come this problem. It's not easy to recognize it. In your normal seismic processing, that's the first assumption you make. You think it's coming from midpoint between source and receiver. That's the midpoint, but actually it's coming, the energy is coming from perpendicular to the interface. That's the interface. This is reflection perpendicular to the interface. Receiver, geophone, seismo cannot directly detect that. Another very problematic drawback, and we studied that, we assume that they are, we consider, actually not assume, we consider them as noises are actually multiples. Multiple reflections are problematic. We call them multiple. They are not true reflections. They are not primary reflections. So what is multiple and what is the other drawbacks? We'll go into details. So this is a non-vertical reflection. What you see if the source and receiver are the same point, it's supposed to go down and received back. That's what I said. However, the reflection actually comes from perpendicular to the interface. That's the perpendicular. Your assumption that it's made here. So it's a mispositioning. You think, okay, it was straight. You think it came from here, deeper, but it came from here actually. So some slight mismatch. This is the real one, and you found it deeper. You found your reflection here, but the real reflection was shallower. This small change, this small mismatch in time create a lot of differences. Maybe you
Why,
think,
doctor, it
okay,
happens?
it happens because of something we call it Fermat principle. Fermat principle states that the rays take the shortest path. It takes the shortest path. What is the shortest path to this reflector? When the first arrival comes, if it takes the shortest path, the first arrival comes when it takes the shortest path. What is the shortest path to this reflector? Is this perpendicular line. It's not this line, it's not this line, it's not this line, it's exactly this line. Goes back. But since I'm not sure if there is a dipping or not, I think my assumption is that things are reflection always coming from the midpoint. This is source and this is receiver, or the opposite. Ignore this spike. That's the midpoint because this is perpendicular. This line is midpoint line is perpendicular to the interface. Unless if there is like a dipping, then where is your line, perpendicular line here? So it goes here and reflected back. The reality is that's the reality. If this layer is dipping. But that's the shortest path. That's the path if the ray takes arrives earlier than any other path. I want the earliest arrival. That's what I care about. That's what I'm listening. Oh, the ray arrived. The energy arrived back to me. It means it's reflected from something. My geophone start recording some energy, arrival energy. Oh, that's why this is a drawback. The principle itself is Fermat's, or the Fermat states that the shortest path, the seismic energy takes the shortest path between source and receiver, and this is the shortest path to be arrived earlier than any other ray path. But we can overcome this problem. This problem is cumbersome, actually. It can be resolved in some way. Another thing we talked about earlier in our subject, I think during the introduction, there might be some multiples. So this is a multiple. Maybe your source is here, that's your source. Your receiver is here. Instead for the energy goes here and reflected back, it goes hit the surface, the interface, reflected back to the surface, and there is no geophone to record it. It goes again reflected back. It's a multiple. That's not a primary reflection. This is a noise, and they happen quite often. There are many methods to detect these things in geophysics. So what happens in the depth domain, in the time domain, you'll find the trace something here for this one. Why? Because this is the double of this one, is the double distance of this one. Have you got my point? This travel time is the double of the primary travel time. Went hit twice. These things, this is quite easy to remove. This type of multiples, the one you see here is easy. Actually, it's the easiest to remove. This is a real signal. Go hit the interface and reflect it back. This is a signal, whereas all of these three are noises. This is interbit. We call it interbit multiple. This is called pig leg multiple, and between two different layers. These two are quite difficult to remove compared to, for example, this simple multiple. Multiple can be removed in different techniques. One of the techniques, especially which can remove this type of multiple, is called deconvolution. So, but we'll not cover that in this course. It's quite cumbersome or needs a lot of math. Actually, we'll not go into detail in math. Deconvolution is a process which can help to remove multiples. That's what you need to understand, at least. And how it's done, that's another topic. A deep detailed topic. But our main concern here is that multiples are things that happens in seismic processing, and we need to try and remove them deploying many techniques, and one of the techniques is called deconvolution. I give you a break for 5 minutes. I relax myself, just 5 minutes. Meanwhile, if you are having a question, you can ask me. You might go and take a cup of tea, cup of drink, relax.
دكتور هنا الحين يعني ديفون واحد يرسل هذه الإشارات ولا عدة؟
There are actually many geophones, not just a simple one geophone. But I'm just here giving you some example how multiple happens. So these are multiples. So if there is a source, here is a source and geophone. Source and geophone. There is a source here and a geophone here. So we'll receive some multiples. Multiples happens whenever there is a strong reflector. Very strong reflectors, they create multiples. Who was talking?
إيه
اللي كان
محمد.
يتكلم محمد. Can you give me an example of a strong reflector? What do you think can be a strong reflector? Sea floor. Good, Ryan. That's amazing. I'm really impressed. Sea floor is good and it can be a candidate of generating multiples. It's a strong reflector. Why I said it's strong? Because the velocity contrast or acoustic impedance contrast, not velocity. Because in reflection, I'm interested on both density and velocity, and acoustic impedance is actually the multiplication of velocity with density. Acoustic impedance is simply I artificial intelligence. It's not artificial intelligence, is acoustic impedance is density times V. So as Ryan said, CBIT is a strong reflector. You see how strong is it? It's a very strong reflector. This is the real geology, and this is the seismic trace, as you see. What do you see here? There are some cable noises, other noises on the surface. These are acquisition noises.
You mean multiples having a strong reflector?
Yes. So where I see the multiple here, you see this one? Oh, sorry, this one. We can show it again. This is exactly same as seabed. So time from here, it's one time. Again here, two times. This is same as this. You see this shape here, it's not very clear. It's resembling this erosion surface. Erosion surface is a surface where rock have been eroded. There is an unconformity. So this is an erosion surface, and they try to find them these things. Yani, they are very candidate, high candidate of reservoirs. The reservoir quality here in channel, this is a channel usually, a filled channel. The porosity is good, the permeability is good. So they'd say, okay, go drill here. But you might be mistaken. Okay, I might go, I found another channel. This is another channel. But it's not a channel, it's just a multiple of this one. So maybe they haven't done deconvolution with this section. Channels are very good candidates to become reservoirs. Why? Because channels are filled with, usually they are filled with good porosity rocks. And nowadays, if you go Wadi, if Wadi is filled, you'll find the rocks are all of same size big rocks. So whenever the rock sizes are same without being filtrated by small particles, they make a high porosity. So we resume. We said multiples are problematic. I'm seeing some multiples here. So here at least one of the strong multiples is seabed. This is the seabed. And where I see its multiple here, I see it. So you should remove this one. Otherwise, you will be disturbing or covering your original traces, your original reflections. There might be another reservoir there at this section, but you are obscuring it because a multiple is on top of it, which is seabed multiple. You have to remove them in some way. And usually the way you can recognize the multiple, especially a multiple like seabed multiple, is double the time. The time from here to here, that's the double of this one. This is strong multiple, seabed, that's the double of this time, time one. This is two-way time because the energy goes and get reflect back. And that's what we call multiples. What multiple are always considered as noises in seismic sections. So all of that, we need something. We are interested in important parameter, which is our main concern, to convert these times or this domain, the X domain, from time to depth. The parameter we need is what's the quantity we need to convert from time to depth? Simply the velocity. So we consider or talk a lot about velocity determination. And the simplest way is something we call it normal move out. Here I have a shot. This type of shot either called split or source method, fixed source method. Why is that? Maybe you have your source here and the geophones all in one line. Maybe I need to draw somewhere else. Can I draw here? Oh, I can draw here with a mouse. Not sure. Okay, next time I try to get a drawing board. Some application where I can draw instead of drawing here. So one of the cases is that there is a source and there are a lot of geophones. This is called off-end. Off-end. Whereas this type, where the source is in the middle, this is called split. So this is a source. I'm having how many geophones? 1, 2, 3, 4, 5, 6. So how much time it takes, you think? What is the time from here to this, for example, to the last, just geophone number 6? How much time is that? What parameters you need? You need the velocity. It's dependent on two things: the distance and the velocity. At least for these two layer case where the second layer is flat. So if you use Pythagorean theorem, because this line from here to here, from S to A, is similar to the line from here, from A to here. Am I right? This one is equal to this one. This line is equal to this line. So let's take the mid one. The mid one, since this from here to here is X, that's capital X. From V, then this point, V to R is X over 2. That's the perpendicular line. This is the middle line is perpendicular. I already told you that the reflections happen at the shortest path. The shortest path whenever the ray hits the interface at right angle. So all of these are at right angles. And you have right now a right angle triangle. I need what things we can apply with right angle triangles. Right angle triangles. Oh, it's right angle in this manner. Pythagorean theorem, yes. We can do Pythagorean theorem. So S to A, SA, let me do it with this one, I think.
البينتر دكتور.
Paint. Let me use paint. Yeah, I think this is good. Can I make some line? Yeah, this is good. How I can delete everything? So here, SA squared equal VA squared plus H squared. Am I right? What is H? H is the thickness of the layer. So this is from Pythagorean theorem. And what I'm interested on this, the travel time. This is basically what? X squared over 4. This is this one. And if I'm interested to know this one, which is then what? Simply square root of x squared 4 plus h2. Divide both of them by velocity of the layer, v of layer 1, v of layer 1. All of it divided by v over 1. What you get? You get t. I'm trying to tell you this, but it's all written here. So these travel times are generating something, some line or some equation, which is the equation of what? If I go back to my, so what is the variable here? How I can delete everything? That's a problematic. I'm not sure how I can delete everything here. I promise next time I'll use some Painter because I'm having problem making notes in these slides. Or maybe I need to remove the background. So I create an equation of hyperbola. The equation you saw there, t equal square root of x squared over v squared plus h squared. This is the equation of hyperbola. At this time t naught, at time t naught, who can tell me what is the time of t? How I can get it? What is the x value at t naught? 0. Yeah, this cancels out. And there is a v. Sorry, I forgot v. There is a v because, so it becomes 2h2 over v. I forgot another thing. Because this is only SA, but I want all the time from here to here again. So it's this section is equal to this section. So it becomes what? 2SA. 2 multiplied, it's 2SA. So I have 2h2. H squared. H squared will go away because it's under the square root. So it's 2h over v. The t time is simply this thing. This is the v time of, that's how you get the velocity of first layer. So the velocity here, the time here is a function of x and a function of velocity as well. So it's function of x, function of velocity. So let me delete everything. So here, if I go back to my equation, first equation, basically T naught, original time, T naught, and some extra time. And that extra time is dependent on velocity and x squared. We come back to this equation soon, how I came to this equation. What you can read from here? What's the missing part from here? What you are interested in here? What the value you are interested? You are interested on velocity. All the other things you can read them from the TX diagram. Where is the TX diagram? This is the TX diagram. We were seeing it before like that. So we were seeing the TX diagram like that before. So this part is similar to this one. So this is the direct, goes asymptotic, and this is the reflection. If you cover one part, if you try to cover this part, let's try to cover it. That's what you were seeing. That's exactly the TX diagram you saw before. But this type of TX diagram happens whenever we do off-end survey. Yani the source is here and the geophone in one line. Split spread survey gives you such type of TX diagram. So what I can read the T naught. I can read the X at specific geophone. There is a geophone here. I can read the X as specific geophone. What's remaining? The remaining part is velocity. I can read T naught, also I can read it, that's the T naught of this reflector. So I can obtain V naught. And V naught, they can simplify it as such. How they can simplify this, I will not go to the details because they apply Taylor series. It's some math geologists, they don't study Taylor series, I believe. Calculus 3 probably. Or calculus 2, you don't study calculus 2, so not go to the details. But the final product is that thing. So you have the X, you have T naught, that's the T naught from this line, and you read this change. The difference, this is delta T, the difference between T and T naught. T minus T minus T naught gives you delta T. That's T naught. This line, which is T naught, here is T naught, and this is normal T, the time at this specific geophone. This is so this is the final equation we need. This is the equation we are interested on to get the velocity. And how we get it, this is the next topic. How we prove this thing. I didn't tell you. But next time or next slides, let's see if there is a time. Yeah, there is time. I'll not make it next time. I will explain to you how we obtain this final version of velocity. I think up to now, everything is clear. What we are measuring, we are not measuring one-way time. We are basically measuring two-way time. So T naught the time at this specific here is what? This time is 2h over 2. Is the ray went and reflected back. 2h over velocity of the over 2, sorry, over velocity over 2 over velocity. So this is T naught. So this is what we explained already, and this is the final version we came. Here we are just applying Pythagorean theorem to this thing. That's h, that's h, that's x over 2, this is h, and this is the interested part. I need but double of that because it goes down and reflect back. So I can tell what is this thickness using Pythagorean theorem. And we already proved this thing. T equals what? T here is T naught plus delta T. T is at here is simply T naught plus delta T. T here equals T naught plus this delta T. And how much is this value? From Pythagorean theorem is simply that. You can prove it again. So this is, if I go do the Pythagorean theorem, I have this one and this one, but I need the double. That's the reason I have 2 here. That's the reason I'm having 2. And divide by, so let's do it again. If you are considering how it was obtained, let me delete everything. Take a screenshot of this one so you see it. So it's SA squared equals what? H squared plus X over 2 all is squared. And I take the square root of this one. SA equal the square root of all of this H squared plus X over 2 squared. There is a plus. But I want all this distance from here up to here. All of this distance is double one distance. Double SA gives you SAR. Double of SA gives you SAR. And I'm interested on SAR. The energy traveled from here, hit the interface, and returned back. So it becomes 2 SAR. Become 2. When I divide this by V, both sides, this becomes distance. The distance of a velocity gives you time. Time becomes then what you see exactly, what you are seeing here, 2 over V1. What you are seeing exactly here. Oh, can I use this one to obtain the velocity? Can I use this equation, discarding this one, to obtain the velocity? Yeah, to obtain the velocity. Is it usable? Who can tell me? How many parameters are there? How many parameters I can read from TX diagram using this equation to obtain the velocity. There is an H. I don't know the thickness of the layer. So how I get the H? So we'll do some math. We'll do some math now. Simple math, not complex math. There are two parameters. What I'm interested in both of them. I'm interested on the velocity of the layer and the thickness of the layer. So this is not helpful. What we will do, we'll do some math. How the math works. This is the original equation I'm provided with. In your book, all of this is totally summarized. Yani they give you the final equation, only this, without going to the details. They said we multiplied squared and got this equation. So we are provided with this equation from the previous slide, from Pythagorean theorem. Let's square both sides. Let's square this part and the other part. That's how I squared them. So I obtain this one and this one. These are the two things I'm interested on. This and this. This is the final one and also this one. Let's do some algebra. What's my algebra? I multiply all of them together. So here, this goes here. This goes here and goes here. This is simple algebra. Am I right? So here, the first thing, multiply here and here. That's the product. 4 goes with 4. I'm left x squared or v squared. Take out the square. Take out the square from here. So it becomes like that. What these things remind you? 2h1 over v. 2h1 over v. It reminds you of what? Who can tell me? What 2h? No. 2h, this inside the 2, huh?
T.
It reminds you of what? T, what T? T naught. T sub naught or T sub O. Replace, this is the travel time at 0 offset, at x0. So it becomes that one, T naught squared x over v1 squared. I'm interested on this one and this one. Let's expand this one. You know how to expand, I believe. And make this one 2. T naught plus delta T multiplied by itself. I'm not interested on this thing. I'm interested in these, the last two things. Let's expand this one and equate this one with this one. So if you expand this one, you try to multiply it. And how you do? T naught plus delta T multiplied by itself. T naught plus delta T. Multiply this here, then here, here and here. What you get this formula. Since I'm interested in these two, after expansion, I think these two T dot squared can be cancelled. I'm remained with these parameters. This is what I'm remained with. 2 T naught delta T plus delta T squared. So this is what I remained with. Let me ask you the question. Here, this is my hyperbola line. Let me it's quite bad drawing. Let me do it again. This is T naught. This is delta T. Delta T is T minus T naught. T minus T naught. And this is at 0 offset, and that is X. This is 0 offset, and the offset is increasing. How much is this value usually in time? How much is it in time? This is time. This axis is time axis. This is distance axis. How much this one is time, in time? Who can tell me? It's a small number. It's a very small number. It's point probably 1. A square of a small number becomes what? Larger or smaller? Squaring a small number, what happens to it? Is it going to be a larger number or smaller number?
Smaller.
Very small number. So for small offsets, this is very small number, so we can ignore it. We can ignore this one, and what we are remained with these two. So everything right now is simple. We can read this from TX diagram. T naught can be read from TX diagram. Delta T can be read from TX diagram. X can be read from TX diagram. So we can obtain V1. We can obtain V1. And they simplify all of this. They can simplify it using Taylor expansion series, Taylor series. So this can be equated if I bring this delta T equal. This is an approximation, yani. X تربيع over 2T naught B1 squared. That's exactly like this one. So in here, everything is simple. This can be removed because, as we said, it's small. You are squaring a very small number. Check TX diagram. Everything is obtainable. We are interested on V velocity. So we can obtain delta T, we can obtain the X distance from source. There is the source. This is the geophone at this distance. Source and geophone. Source, geophone, that's the geophone. And I need this X, that's the X. I can read it from my geometry. Already I have it in TX diagram. And I have T naught, it's read from here, and I have also delta T. But there is another problem. What do you think that problem is? It's not a problem. It's a complication. You are doing it for one layer. It's for one layer. This thing becomes more complicated for multiple layers. However, I stop here We'll continue with multiple layers next time, next week. Discard all chains. I'm in good spot, so we spent 3 weeks. This is the first week. We spent 3 weeks on these slides, I believe. So the next time we'll talk about multiple layers. And I give you an exercise on how to do this in multiple layers. There is a velocity, we call it RMS velocity. Yani the velocity you read the time to up to a layer, specific layer, and the time from here up to there, time for the ray goes to the third layer, time the ray goes to third layer and reflected back. It depended not on one velocity, it depended on 3 different velocities. And those, the sum of these velocities is called RMS velocity. And this is how you do it, how you get the RMS velocity. And we'll work in your assignment. You work how to get the thickness and velocity of each layer for multiple layer case. Then we talk another thing. We'll have another assignment. They are very short. You will do something called velocity analysis, something similar to this. So this is a velocity analysis. We'll talk about velocity analysis. And the final thing, because if we move along, the final thing, you are seeing already some sections, seismic sections. I move forward. This is a seismic section. You will do some interpretation in your project. So there are 3 different, as I said earlier in the beginning, there are 3 different labs, or not lab, basically assignments or projects related to seismic reflection technique. This week is week 7. Next week you have your first exam or midterm exam. Do you have any questions related to what we have discussed so far in seismic reflection technique? Any questions? Next time we'll talk about multiple layers. And we'll talk about stacking. What's stacking? Stacking is something different than the stacking, vertical stacking, where I repeat the shot. It's totally different in here, in seismic reflection technique. Then we talk about what are the spread types, shot types. And there are many things we talk about, and velocity analysis, and how they do the velocity analysis. So you have 2 labs. One is how to do semblance and check your velocities. If you pick the correct velocity, these reflectors, the NMO, they are upside down. You see how many layers? 1, 2, 3. There are many layers. Each one is producing a hyperbola. These are hyperbola. This thing is similar to what you see here, except the one there is one-sided. What I mean by one-sided, I mean one side is covered. You see one side. It's one-sided because it's off-in survey. It's not a split spread survey. This is split spread survey. So what you see, this is these are all different reflectors, and each reflector, the line of reflector is hyperbola. If you apply NMO, correction, it's going to be flattened. So our objective, final objective, is to remove this thing, make it flat, because the earth really is flat. The earth itself is flat, so I need to make these things flat. All the objective of velocity analysis, velocity determination, is to flatten these hyperbolas. We'll talk about that next week in more details. If you don't have anything, any questions, first of all, I stop the recording.